Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 46, and this problem asks us to determine the products of A to D and indicate their stereochemistry. So let's start with A. So A, we have this electrophilic compound. We know that this is an electrophile. Why? For two reasons. Well, there's a leaving group bound on it, so we know that an electrophile needs a leaving group to act as electrophile, and two, we're adding a carb anion, which is very, very, very nucleophilic. So right away we know this is a nucleophile, therefore this must be the electrophile. So we can imagine that, let's see what we have. We have a leaving group bound to this carbon. This carbon is a primary carbon with two of these bonds being hydrogen. Deuterium is just an isotope of hydrogen with two neutrons, or actually, sorry, one neutron to make a mass of two. And we have one R group, which is a non-hydrogen or non-hydrogen isotope atom. So we know that an SN2 mechanism can be allowed here following our SN2 or SN1 rules. So we know that we can do a 180-degree backside attack to make a new bond. When you make a bond, you need to break a bond. So the chlorine leaving group will fall off. But remember, a key distinguishing feature in SN2 mechanism is that you have an inversion of stereochemistry. So how do we invert the stereochemistry here? Well, we can draw the product of A as 1, 2, 3, 4, 5. So we have 5 carbons, and now the chlorine is going to be replaced for our new nucleophile. We get this chlorine ion byproduct here. But we need to invert the stereochemistry. So how can we invert stereochemistry? Well, changing the positions of any two atoms on the molecule will invert your stereochemistry. So how I like to do it is I like to change the atoms or the substituents that are coming out of the page as a wedge and into the page as dashes. If you just change these two positions, you will invert stereochemistry. So in the starting material, hydrogen's coming out. So that means in a product, deuterium is going to be coming out. And in the starting material, deuterium is going in. That means in a product, hydrogen has to be going in. So this is our substitution product here. In B, once again, you have a similar reaction mechanism going on here. But if you guys can tell, you have a carb anion here being a nucleophile, and then you have your electrophilic carbon. So if I were to make my SN2 reaction here, I would get the product of B, 1, 2, 3, 4, 5. But now the chlorine is going to be replaced for my nucleophile. And then, but now here's the thing. So remember, to invert your stereochemistry, you need to change the substituents of two, change the location of two substituents. Well, that's only the case for chiral carbons, chiral center. So what a chiral carbon is, or a chiral center is a carbon with 4 unique substituents. So deuterium and hydrogen are unique. They're different from each other. And this guy here is unique and the chlorine is unique. But in B, we have 2 hydrogens attached to this electrophilic carbon. So this is not a chiral center. So there cannot be any inversion of chemistry, stereochemistry here, because there is no stereochemistry here. But what does exist is we retain the stereochemistry of these substituents that are downfield on the molecule because they're not involved in any chemistry. They're just hanging out here while all the chemistry that's going on is at this terminal end of this molecule. So let's see what we have. We have an epoxide with equal protons on each side, and we have a strong nucleophile carbanionic alkyne. So what we can do is we can identify that the nucleophile will attack on the opposite side as our epoxide, and it will attack on the least substituted side. So in this case, both of them are equally substituted. So we can attack from either side with equal probability. So either here, when we make a bond, you break a bond. So this oxygen will pop up. Hydrogen in water will protonate this oxygen to make an alcohol. So now we get our alcohol here. And then you get your nucleophile attached here. And then what you will get is an inversion of stereochemistry, actually. So what you're doing here, actually, stereochemistry is not inverted, it's retained because it's not actually an SN2 mechanism. So hydrogen on this side is here. This carbon is here. On this side, you have your methyl group and hydrogen down here. So this is one product, but with equal chance, your carb anion can attack on this side, making a bond. When you make a bond, you break a bond. This gives O-, but O- will be protonated by water to give an alcohol. Then you get your alkyne product here. Then you get your methyl group coming out of the page, your hydrogen going into the page, and this side, same thing, hydrogen coming out of the page, methyl going into the page. But if I were to flip this molecule around, I would see that I just formed identical structures to this. So these two products are identical. There's no difference between them. These are identical. So it doesn't actually matter which side this attacks on. So now let's see for this example here. So once again, we have equivalent carbons. So 50-50 chance it can attack on this side or this side of your epoxide. So if it attacks on the blue side, you get the blue product. And then remember, your stereochemistry is retained. And then on the green side, we would get on the green side, you get the green product. So now you may be wondering, well, are these the same products, or are these enantiomers, or what are these? Well, this is where your molecular model kits come in extreme use. So if you were to draw each of these and you flip them such that your alkynes would overlap. So if I would take this and I would flip it such that this alkyne would overlap this one, I would see that when I flip this carbon originally is coming out of the page. That means after I flip it, it'll be going into the page and then superimposing this. So and the blue carbon's coming out of the page, but when I flip this, carbon will going into the page. And you can see the hydrogen will coming out of the page while this hydrogen is going into the page. And if I were to flip this side, this molecule with the carbon coming out of the page, this methyl group coming out of the page, if I flip it, then it'll be going into the page, but in the blue, it's coming out of the page. So clearly, these are non-identical, non-superimposable mirror images of each other. So these are what we call enantiomers. So they're unique stereo products.